Swayam Prabha. Digital India. Educated India.
Welcome to the 20th lecture in our particle characterization course. In the previous lectures, we have been focusing on particles that are suspended in a medium and the types of interactions that these particles have with the surrounding medium. In particular, we have been looking at aspects of particle to surface adhesion and also removal of particles from surfaces. Now, in this lecture, we are going to focus on interparticle adhesion, that is adhesion between particles that are suspended in a fluid. Another name for this is cohesion. The cohesive behavior of particles that are suspended in a fluid is very crucial in determining particularly the flowability characteristics of the suspension. In many industries, we have situations where particles are suspended either in a liquid or in a gas, and they have to be made to flow in a certain direction at a certain velocity at a certain flow rate towards a receptacle or another surface and so on. So, it is very important for us to understand how this system is going to behave, that is the combination of the fluid and the particles that are suspended in the fluid. And it turns out that the degree to which particles that are adjacent to each other try to interact with each other determines the flow characteristics of the suspension itself. And so, we need to understand the reaction mechanisms as well as the interaction forces between adjacent particles in order to characterize how the suspension will flow. Now, when we look at interparticle forces of attraction and repulsion, many of them are common to what we had discussed earlier in the context of particle to surface interactions. For example, van der Waals forces that we discussed in detail early on in the context of particle to surface interactions are obviously also important in the context of particle to particle interactions. The van der Waals forces in the case of a particle to particle interaction can be written again in terms of Hamaker constant A132. If you recall, our definition of 1, 2 and 3 is 1 will be in this case particle 1, 2 will be particle 2 and 3 is the intervening medium, liquid or gas. So, Hamaker constant multiplied by the distance of separation between them also enters your equation as 12 times if the distance is some S0, it is divided by 12 times S0, and the diameter of the particles, essentially representing them as equal sized particles, will again enter in the numerator as a size term. So, just like the van der Waals force of interaction between a particle and a surface, the force of interaction between two adjacent particles also shows a linear dependence on the particle size. Now, this is for the case where the two particles are of equal size, particle size dp. When you have two different diameters dp1 and dp2, then you essentially define an equivalent diameter, a mean diameter. So, if you have two particles that are of sizes dp1 and dp2, you can define an effective diameter 1 over dp bar, which is equal to 1 over dp1 plus 1 over dp2, and that will serve as the effective diameter that governs the van der Waals force of interaction between these two particles. So, if you look at the van der Waals force of molecular interaction, the mechanisms and the forces are really not very different from the forces of interaction between a particle and a surface. Similarly, if you look at electrostatic forces, and again let us say that you have two particles of charges q1 and q2, then the electrostatic force of interaction between them will be q1 q2 by 4 pi epsilon r epsilon 0 times s squared, where q1 and q2 are the charges on the two particles, epsilon r is the dielectric constant of the medium, epsilon 0 is the permittivity of free space, and s is the distance of separation between the centers of the two particles. So, again electrostatic forces between two particles are very, very similar in their behavior to electrostatic forces between a particle and a surface. So, what is unique about particle to particle interactions? Why do we need to study that differently from particle to surface interactions? The primary reason for this is this cohesive behavior. What do we mean by cohesive behavior? When you have a suspension where you have a fluid and you have various particles that are suspended in the fluid, there are various modes of interaction between the adjacent particles. In the simplest case, they do not even know that each other is there. So, the behavior of every particle can be taken to be independent of the behavior of any other particle in the system. But in reality, there is always a tendency for two particles that are near each other to try and find each other. And when that happens, you first start forming a bridge between two adjacent particles. It is called a liquid bridge. And when that happens, when you have bridging between two particles, this is called the pendular state of cohesion. What will happen next? A third particle will be brought into this system. So, when you have three particles that are bridged by the surrounding fluid, that is called the funicular state of cohesion. And finally, the next state would be one that involves, let us say, 4 particles. When that happens, that is what we call the capillary state of cohesion. Now, when this bridging extends beyond 4 particles and starts encompassing a larger number, so more than 4 particles now begin to be bridged by the surrounding fluid, that is called the droplet state of cohesion. And it turns out that the cohesive behavior between the particles very much depends on what state of cohesion they are in. For example, when you have no cohesion, as I said, that is the simplest case. So, each particle can be treated as a hard sphere that is moving on its own in the surrounding fluid. When you have two particles that are bridging, pairwise bridging, the pendular state, that is a state of minimum cohesion in the fluid. So, there is cohesive behavior, but it is reasonably mild. As you go into the funicular and capillary phases, the extent of cohesion begins to increase, and therefore, you have to start treating the particle phase virtually as a continuous phase that is present within another continuous phase. In other words, you have to start following the two-phase model in order to characterize the behavior of such suspensions. And by the time you get to the droplet state, where there is larger than 4 particles that are essentially bonded together it becomes highly cohesive behavior, and you cannot describe the motion of such a suspension without understanding how this droplet behaves as a separate phase that is contained within the macroscopic fluid phase. So that's what makes cohesion interesting. These are behaviors that you don't normally encounter in the case of particle to surface interactions. Now, in terms of forces of interaction, cohesive forces we already talked about van der Waals forces and electrostatic forces. In addition, you have what are known as capillary forces. Now, the capillary force itself has two components to it. One is surface tension related, and the other is pressure differential related. In addition to that, you have viscous forces, and here again you can subclassify them as normal and tangential. And finally, you have spring like forces, and this also you can classify as normal and tangential. So, we will look at what these are in more detail, but the point is that in order to describe cohesive bonding between two particles that are in solution, you have to characterize all of these forces, and the net force that is acting will be a sum of all these forces that are acting on particles that are suspended in a solution. So, let us look at forces 3, 4 and 5 in a little more detail. So, what do we mean by capillary forces? Let us take the situation where you have particle 1 and particle 2, and there is a liquid or fluid bridge between them. Now, the angle to the centroid of the particles that the meniscus makes, this angle is called beta. Are we still on? Okay. And the as the angle beta becomes smaller and smaller, as beta tends to 0, the force essentially basically this meniscus will become thinner and thinner. So, as you can imagine, there will be less and less cohesive bonding between the forces. So, as beta tends to 0, F capillary will tend to 0, and as beta tends to 90 degrees, F capillary will tend to its maximum value. So, the 90 degree corresponds to the case where essentially the liquid bridging extends all the way to the outer perimeter of the particles. So, beta is now 90 degrees. So, this represents the case where we have complete wetting. So, this is a case where you are into the so called capillary or droplet regime of cohesion. So, whether you are in the pendular or funicular or capillary or droplet state depends a lot on this parameter beta, which is also called the half fill angle or the angle of cohesion between adjacent particles. So, when we look at the forces now between these two particles, there are really two components to it. One is just due to the surface tension that is associated with the fluid that is bridging the particles, and the other is associated with the pressure differential delta P across the fluid to air interface that surrounds this suspension. So, you have to split the capillary force into its two components, F surface tension plus F pressure differential, and you write those as 2 pi rp gamma times sine squared beta plus pi rp squared delta p sine squared beta, where 2 pi rp gamma sine squared beta represents the surface tension force and pi rp squared delta p represents the circumferential force multiplied, which is the pressure differential multiplied by the circumferential area of the particle. Or you can simplify this and write it as 2 pi rp gamma sine squared beta times 1 plus rp delta p over 2 gamma. Now, this parameter rp delta p over 2 gamma is represented as h star, and it stands for what is known as the dimensionless mean curvature. Which is a parameter that can be extracted from the basic Laplacian equation governing the elastic behavior of these particles in suspension. So, the expression for the capillary force itself can be written as 2 pi rp gamma sine squared beta times 1 plus h star, and it can be evaluated for essentially any pairwise combination of particles that are suspended in a fluid. Now, the viscous forces again can be split into a normal force and a tangential force. The F viscous normal, the normal contribution of the tangential force is given by 6 pi mu rp v normal times rp over s, where rp again is the radius of the particle, s is the distance of separation between the particles, Vn is the relative normal velocity between two particles that are in suspension. So, if you have a particle, two particles, that velocity itself can be deconvoluted into a tangential velocity and a normal velocity, and the delta between the normal velocities of the two particles enters this equation as Vn, and similarly the delta between the tangential velocities enters the equation for the tangential viscous force, which is given by 6 pi mu rp times Vt times 1 plus 0.5 logarithm of rp over s. So, in all of these equations, one of the things you will notice is that if you look at the equations we have written so far, most of the adhesive forces still have the linear dependence on diameter. Just like we described earlier, when you have particle to surface adhesion forces, where the adhesion force essentially scaled as the size of the particle, you will see that if you look at the cohesive forces as well, the surface tension force clearly has an rp dependence. However, the pressure differential, because it is an area effect, has a rp squared dependence. So, the net of this term plus this term will give you a dependence of capillary force on particle size that is somewhere between 1 and 2, depending on whether the surface tension forces are dominant or the pressure differential forces are dominant. So, in the one case where the h star term is very small compared to 1, you will get a dependence of linear dependence of the capillary force on rp. In the case where h star is much larger than 1, you will get a rp squared dependence, and for any value of h star that is intermediate, you will get a dependence that is somewhere between 1 and 2. If you look at The viscous forces, on the other hand, there is clearly an RP squared dependence of the viscous force between two particles. Now, what that means is, as particles get smaller, the viscous forces will drop off much faster compared to the capillary forces, that is the normal viscous force. However, the tangential viscous force, which essentially relates to how particles are moving relative to each other in the direction of flow. Now, again, when we say normal and tangential, what we mean is, if your flow direction is like this, the normal force is the one that applies normal to the flow direction, and the tangential force is what applies tangential to the flow direction. So, the viscous forces, the normal viscous force goes as the square of particle size, whereas the tangential viscous force essentially goes as RP times logarithm of RP. So, here again, if you look at the total viscous force and look at the particle size dependence, you will reach a value that is somewhere between 1 and 2, again depending on whether the tangential term is dominant or the normal term is dominant. Now, just like we had reported some empirical data on surface to particle adhesion, which suggested a linear dependence on particle size as well as on the relative humidity that is presented in the system. Similarly, there is quite a bit of work that has been done to look at agglomeration of particles in suspension from a purely empirical viewpoint, experimental. So, you take a bunch of particles, put them in suspension, monitor their number over time, total number of particles. As the total number decreases as a function of time, obviously there is more cohesion and agglomeration going on. So, the rate of reduction in total number of particles as a function of time is a measure of the extent of cohesion that is present in the system. Another way to track it, of course, would be to look at size. If you track the mean size, that size will keep increasing as a function of time if there is cohesion. So, there are two ways in which you can detect the presence of cohesion or absence in a suspension, and they both basically depend on plotting as a function of time. So, in one case you can plot n of t. So, let us say that this is time equal to 0 and the corresponding number of particles of any size. So, that is n at t equal to 0. What will happen is that if there is no agglomeration happening, then what dependence would you expect? It will be constant, right, as a function of time. So, if this is your n at t equal to 0, in the absence of cohesion, this number will remain constant over time. However, as cohesion starts to happen and as particles start to agglomerate, you will see that there is a net reduction in the number of particles as a function of time. And similarly, you can also plot particle size dp as a function of time. And here again, if let us say that this is your particle diameter at time equal to 0, let us say that this is your diameter at time equal to 0. If there is no cohesion, it will remain constant over time, whereas if there is cohesion, that particle size will keep increasing in some fashion. So, with cohesion you will see an increase in the mean particle size of the system. So, this behavior where there is a monotonic increase of particle size with time or a monotonic decrease in the number of particles with time is clearly indicative of cohesive phenomena that are happening in your suspension. And in fact, there is an empirical equation that governs the relationship between particle counts at various times. So, if you take 1 over n as at time t, this is equal to 1 over n at t equal to 0, plus 4 kT CCT over 3 times mu, where n of t is the number of particles at time t, n at t equal to 0 is the number of particles at time equal to 0, plus k is the Boltzmann's constant, T is the temperature, lowercase t is time, mu is viscosity, and Cc again is the Stokes-Cunningham slip correction factor. And if you recall, I had mentioned that this is roughly proportional to 1 over dP. So effectively you can write this or rewrite this as some constant k prime and have the particle diameter in the denominator. So what is the implication of this equation? What does this tell us about agglomeration kinetics? What are the parameters that it depends on? Obviously, I mean, if you take 1 over n of t minus 1 over n at t equal to 0, this is now going to be equal to k prime kt t over 3 dP times mu. So if you examine this equation, which by the way, as I said, is empirical, what that means is people have done thousands of experiments and actually recorded the data, and they have done a regression analysis of the data to determine how particle counts change as a function of time, and they have come up with this expression for various systems. What this tells us is that as temperature increases, there is increasing agglomeration. As time increases, there is increasing agglomeration. As particle size decreases, there is increasing agglomeration, and that is why nanoparticle systems in particular are very susceptible to cohesive behavior. There is an excessive tendency for nanoparticles to agglomerate in solution and form clusters. And finally, as viscosity decreases, there is an increasing tendency to agglomerate. So if you want to keep particles suspended and dispersed in solution, what this tells you is, actually it gives you a lot of clues about how to keep particles separated in suspension. Use high viscosity liquids. So is water a high viscosity liquid? Compared to some, but it's not the highest viscosity liquid you can find. You can add additives to it to increase its viscosity. Particle size, probably you cannot play with too much. I mean, you need nanoparticles, right? However, temperature, now that's interesting. Essentially by lowering the temperature, you can keep the particles more uniformly dispersed. So if you are trying to maintain a nanoparticle suspension and ensure that the particles stay dispersed, what do? You freeze it. I mean, that's the simplest thing to think of, because when you freeze it, the particles are now held where they are, right? And then just before you are ready to use the nanoparticles, remelt the suspension. Alternatively, even if you don't freeze it, lower the temperature so that it's close to the freezing values, and that will reduce the mobility of the particles and thereby prevent agglomeration from taking place. Time, obviously the longer you let the suspension sit, the more tendency for cohesive behavior to happen. So if you want to use a nanoparticle suspension, you use it as soon as you make it, or alternatively you make the suspension just when you are ready to use it. So it's like a just-in-time process. If you let any nanoparticle suspension sit for any length of time, you are going to see severe cohesive behavior. You will see particles disappear and you will see particle sizes increase because of cohesion, agglomeration, and so on. So again, the interesting thing here is that when you look at extent of agglomeration, particle size sits in the numerator. Now what that tells us is that the force of agglomeration between particles is actually scaling inversely with particle size, right? So this would tell you that F cohesion in general goes as 1 over dP. But if you look at the equations we have formulated, we are not really getting that trend anywhere, right, so far. They are all either linearly dependent to particle size or linearly dependent on some power or exponent of particle size. So, how do you reconcile that with this behavior that we know intuitively finer particles will find each other and adhere much faster compared to larger particles. So, just like the the apparent conflict that we discussed earlier in terms of particle adhesion and particle removal, this is something else to kind of ponder. Is there a theoretical reason for this? Can we explain this, or is it completely anomalous behavior? So, we'll come back to this later. Okay, so we have talked about van der Waals forces, electrostatic forces, capillary forces, and viscous forces. What do we mean by the spring forces? When you have two particles that are in suspension, they behave as if they are attached to a spring. There is in the normal direction, there is a compressive force associated with this pair of particles. Over time, as particles start moving away, let us say that particle 1 stays where it is, but particle 2 has now moved over here, then there is also a tangential spring force that applies, Ft, which actually has a tendency to bring them back together. Both the Fn force and the Ft force are essentially attractive forces. The particles are constantly trying to, as you try to move them apart, they want to stick together, and so they both lead to cohesive behavior. The higher the normal force and higher the tangential force, the greater will be the extent of cohesion. So, this force, the compressive force Fn, can be written as a Kn times alpha to the power 3 by 2, where alpha is dP1 plus dP2 minus S12, where dP1 and dP2 are the diameters of the particles and S12 is the distance of separation between the centers of the particles, and this parameter Kn is given by 4 by 3 times dP star times square root of E star, where E is the Young's modulus dP star is calculated again by taking 1 over dP star equals 1 over dP1 plus 1 over dP2, and E star is calculated as 1 over E star equals 1 minus nu 1 squared over E1 plus 1 minus nu 2 squared over E2, where the nu values are Poisson's ratios. So, if you look at the expression for the normal force, the key dependencies are on the sizes of the particles, the distance of separation between the particles, and on the associated parameters that govern the elastic behavior of the system, particularly the Poisson's ratio and the Young's modulus for the two particles. If you look at the tangential component, Ft is related to Ft0, which is the time 0 value of the tangential force, that is basically where the two particles are virtually below each other. So, there is no tangential displacement, and then as soon as the displacement starts to happen, this kicks in. So, it is actually a minus kT times delta S, where delta S is the tangential distance of separation between the two particles. Delta S of course is related to time delta t by the equation delta t times Vt. So, if you take a time differential delta t and multiply it by the tangential velocity, again the relative tangential velocity, that gives you the distance of separation at time equals t. So, this is a relative value. So, basically the picture that you have here is when you have two particles that are adjacent to each other, they also have a tendency to have a compressive interaction between them as well as a shearing interaction. So, this tangential interaction can also be written as a shearing force, but in this particular case when you have two particles that are suspended in solution, the shearing force is one that essentially tries to bring them back together, just as the normal force is a compressive force that tries to force the particles together. So, again going back to that list we had, what you can see is virtually all of the cohesive forces are attractive in nature. Van der Waals forces are attractive, surface tension forces, pressure forces, viscous forces, as well as the spring forces are all attractive in nature. The only force that is potentially repulsive is electrostatic forces. So, this again gives you a lot of clues about how to keep particles separated when they are suspended. Since all the forces of interaction, virtually all of them are attractive in nature, the first thing you have to understand is there is going to be an overwhelming tendency for the particles to attract each other. So, if you want them to repel each other, one way is to charge them. If you impart a light charge on all the particles, then that F electrostatic can be made to be repulsive in nature. So, let us sum up all the forces that act in cohesion. So, you have van der Waals plus electrostatic plus capillary plus viscous plus compressive plus shearing. So, of these van der Waals, capillary, viscous, compressive, shearing are all attractive in nature. However, this can be attractive or repulsive. So, by inducing a large charge on the adjacent particles and ensuring that they are of the same sign, you can set up a repulsive force which can balance or actually overwhelm all the other contributions. So, if I am trying to minimize cohesive behavior, one of the techniques I would look at is using electrostatic effects to provide a repulsive force in the system. What else can I do? Well, we know that these forces are attractive, but you can make them weaker. For example, you have seen before that van der Waals forces can be reduced by simply immersing in a liquid medium. So, if you are trying to again keep particles segregated, you do not keep them as a dry powder. A dry powder has a much more severe tendency to agglomerate than a wet slurry. So, suspend the powder in a liquid so that you can minimize forces of van der Waals attraction. Later on, when you get ready to use the powder and you need it in dry form, you can always evaporate the liquid where they are suspended. Of course, to do that you are better off using a high volatility liquid which can be easily evaporated. Water is not an easy liquid to evaporate, but there are many organic solvents that you can suspend particles in which have a high volatility, and therefore you can easily recover the particles in the dry state whenever you need them. In terms of the capillary forces, surface tension is an important component. How do you minimize surface tension? By using surfactants, and that is why the use of surfactants is again widely resorted to minimize cohesion in suspensions. Now, there are two ways in which actually surfactants help. One is by reducing the surface tension forces, and the other is by reducing the hydrophobic hydrophilic interaction forces. By the way, that we haven't talked about here, but refer back to our discussion of interaction between particles and surfaces. The force of hydrophobic / hydrophilic interactions is another major contributor. And by the way, this force can also be made attractive or repulsive when you have particles in suspension. So, one way to reduce cohesive behavior of particles suspended in a liquid is that if you have two particles and they are suspended in liquid and they have a high cohesive force between them, the use of surfactant helps in two ways. One is by reducing surface tension and reducing surface tension forces. The other is if you can get that surfactant to actually coat on top of these particles. So, for example, a simple non-ionic surfactant can be made to form a coating layer on the surfaces. Then what will happen is the hydrophobic portion, as we saw earlier in our discussion on surface interactions, the hydrophobic portion will attach itself to the particle, the hydrophilic portion will stick out. Similarly here, the hydrophobic portion will attach to the particle and the hydrophilic portion will stick out, and these two will actually repel each other because they both have a tendency to want to attach themselves to water. And therefore, surfactants help in two ways. One is by reducing surface tension, and the other is by providing an active coating on top of the particles, which can be made to provide again a repulsive interaction based on the hydrophobicity / hydrophilicity of the surfactant layer compared to the medium of suspension. So, you have to choose a surfactant appropriately for the liquid in which the particles are suspended. For example, if the suspension medium is water, then a simple non-ionic surfactant will work in this fashion. But if the particles are suspended in a hydrocarbon solvent, then the same technique will not work. And in fact, in this case, the coating material should preferably be some low surface energy material, like for example a fluorocarbon, because in that case a fluorocarbon, because it has low surface energy, will reduce the force of interaction between adjacent particles. So, the way that you can reduce particle to particle cohesive forces is by the use of surfactants or detergents or solvents is in two ways. One is to affect the hydrophobicity and hydrophilicity and set up a repulsion mechanism. The other way is keep the attractive force, but reduce its magnitude by reducing the surface energy of the particle by providing a suitable coating material. So, if you have the surface that is coated with a fluorocarbon by definition has very low surface energy, which implies very low force of attraction. As we have discussed earlier, the surface energy of a material relates to its Hamaker constant, which relates to its van der Waals force of adhesion. So, a fluorocarbon works by producing a low surface energy surface. A surfactant, on the other hand, works by lowering surface tension and by providing hydrophobic / philic repulsion. Okay, let us come back to this equation. What else can we affect to minimize cohesive forces? We have talked about what we can do to minimize the van der Waals force. We have talked about what we can do with the electrostatic force. We have talked about the capillary force. By the way, in terms of reducing capillary interaction, another way in which we can reduce the tendency to agglomerate is to reduce the initial concentration of particles. The lower the concentration of particles, the N0 value, the lower will be the cohesive phenomena that takes place afterwards. So in a highly dilute slurry or suspension, the tendency for cohesion, the tendency for agglomeration will be significantly lower for many reasons. One, the simplest being the interparticle distance is much greater in a dilute suspension compared to a concentrated suspension. So it's more difficult for the particles to find each other and agglomerate. So that gives us another option, that if you want to maximize cohesion, increase the concentration in the slurry. If you want to minimize cohesion, you minimize the concentration of particles in the slurry. We talked about hydrophobic, hydrophilic forces. Viscous force, basically if you can reduce the viscosity, then that can actually result in reduced cohesion, right. Compressive force and shearing force, here essentially what you can do is, when you try to keep the particles apart, obviously the distance of separation plays a key role. The farther apart the particles are, the less is the compressive stress between them. So this again says lower the concentration. If you reduce the concentration of particles, the interparticle separation will naturally be greater compared to if you have a more concentrated suspension. You can also look at parameters like the Poisson's ratio and the Young's modulus and see how they can be tweaked in order to minimize these spring-like forces. But in terms of the tangential or shearing force, essentially what this equation tells you is, if there is relative motion between the particles, there is a tendency for them to jerk back together. Now this actually gives us a clue as to why nanoparticles have greater agglomeration tendencies, because Brownian diffusion, which is the primary mechanism of transport for nanoparticles, has an inverse dependence on particle size. So as particles get smaller, Brownian diffusion values get larger. So if you have two adjacent particles, the distance by which they are separated as a function of time will be greater in the case where particles are smaller, because they tend to move over larger distances. And since it's a random walk, they are not going to move in the same direction. So as particle sizes get smaller, this distance of separation delta s as a function of time will get larger. Basically this relative velocity Vt will scale as 1 over dp. As the particle size becomes smaller and smaller, the relative velocity between adjacent particles will become larger, and therefore the Ft value will quickly increase. And so the primary reason that particles in suspension have a greater tendency to attract each other as the particle size gets smaller is this tangential or shearing interaction. Now there are other reasons as well, and we will discuss them when we talk about the transport characteristics of particles, but the key thing to understand right now is that finer particles always have a greater tendency towards cohesion. Now that has a lot of implications for, again, the flowability of suspensions or slurries. It's always more difficult to handle flows that involve fine particles compared to coarse particles. So we'll stop this lecture at this stage. In the next class we'll talk about flowability characteristics of suspensions, what are the properties of particles, characteristics of particles that affect flowability of suspensions, and how they can be optimized for various applications. Any questions on what we talked about today? Okay, I'll see you in the next class then.